Conway's game of life is less of a game and more of a simulation. Essentially, it's a cellular automaton that uses 3 simple rules to create exceedingly complex output. Now, if we wanted to simulate the roughly 5,000 cells on screen, we could pretty easily do that with a tile map. But what if the simulation space was much larger? 10,000 cells? 50,000? 100,000? What if the simulation space was 1,000,000 cells? If we used a tile map for this, we would have to measure our performance in seconds per frame instead of frames per second. So how are we able to simulate all of these interactions without destroying our performance? Let's get after it. Since we can't use a tile map to render our grid to the screen, we need to come up with a custom solution that provides the same sort of effect, but using a shader. So what do we know? We know we want to render a grid, and we know that a grid is just a 2D array of cells. And since our cells can only exist in 2 different states, on or off, we can express them as bits, 1s and 0s. What is the best way to store a 2D array of bits that can be easily consumed by a shader? I feel like there's probably some sort of standard data container that we can use to store a map of bits. If we assume a black pixel represents a 0 and a white pixel represents a 1, this should work nicely. So let's write a shader that can take an image that looks like this and map it to a grid that looks like this. Alright, so here we are in a brand new Godot project, and the first thing we want to do is create a new 2D scene. And I'm just going to rename this root node to .matrix. And then let's just save it. Here we go. And the next thing we're going to want to do is change our project settings a little bit. So we're going to come up here to project settings, and down here in the rendering environment, we're going to change our default clear color to black. And we're also going to go to display window. We're going to change our viewport width to 1920 and the height to 1080. Perfect. Now let's make that shader. So we'll just go to new resource. We'll create a shader. And the mode of the shader is going to be canvas item. And we'll call this .matrix.gd shader. Great. Now let's open it up. The first thing we need to do is set up some variables. So I'll just quickly fill these out and then we'll talk about them. If you've never worked with shader code before, some of this might look a little strange to you. In particular, the keyword uniform and the type of sampler 2D. Uniform is a storage qualifier that tells our shader this value will not change from one invocation to the next inside of a particular rendering call. Now we're going to discuss invocations a little later on, but right now the only thing you need to understand is that this keyword allows a variable to be modified in the inspector. A sampler 2D is just a texture. So we need 3 uniform sampler 2Ds. We need one for our unlit texture. We need one for our lit texture. We need one for our binary data texture. We're also going to need this variable called grid width, and this is going to control the number of cells in the grid horizontally and vertically. We also need a variable to tell the shader how large these cells are. And we need this variable for fade distance, and this is because we're going to implement a fading effect around the edges of our .matrix display. Alright, so we're going to place all of the logic for our shader inside of this fragment function. And the first thing we need to do in here is calculate the total size of the grid in pixels. The next thing we need to do is scale our UV coordinates to match these grid dimensions. And then we're going to have to calculate the index of the cell based on those scale coordinates. And now we're going to have to check if the current UV coordinates are inside the bounds of a cell or not, because if we don't do this, we're going to get some weird clipping issues. Next, we're going to calculate our normalized UV coordinates for the binary data texture. And we're going to read the binary value from the texture. And then we're going to determine if the binary value represents a white pixel and then we're going to calculate the distance to the nearest border for our fade effect. And then we're just going to default the color of the cell to the colors in our unlit texture. And we'll check if the cell is white and the UV coordinates are inside of a cell. And if it is, we will set the color to the pixels in the lit texture. And next, we're going to interpolate our alpha value logarithmically based on our distance to the border. And lastly, we'll just set the color. And that should be all we need. All right, back in Godot, we have a few things to set up before we can use our shader. First, we're going to create a new Sprite 2D node and rename it to Renderer. And then we're going to assign the default icon texture to the sprite. And we're not actually going to see this texture. We just need to make sure that we have a texture so that we actually have some input pixels for the shader. The next thing we have to do is change the scaling factor to 15. And this is because this icon image is only 128 pixels square, but our window resolution is 1920 by 1080. So we need to make sure the texture we use is square and that it has enough pixels to fill the width of our window. If we want to use a different window size or a different texture, we can calculate the scaling factor by dividing the width of our window by the width of our texture. So let's just center this up real quick. That's going to be 960 and 540 because that's the center on a 1920 by 1080 resolution. And we'll just lock this down so we don't accidentally move it. All right, great. So now we're going to come to the material and we're going to create a new shader material. We just click on this and we're going to use the shader we just created. And now it's all black. So we got to go down to the shader parameters and let's set our grid width to 1024. This is the width in pixels of our binary data texture. Now you can see that it's all white, and if we zoom in, we should be able to see that fade effect around the edge. Perfect. All right, and now we need some textures for our cells. So we're going to need the unlit texture and the lit texture. And I just made a few simple ones in Photoshop, and they'll be available on GitHub, or you can make your own. Just remember that they should be small and square. So let's assign this unlit texture and assign the lit texture. Great. Now if we zoom in, you can see that we're starting to get the resemblance of a dot matrix display here. So all the cells are lit, and that's because we haven't actually given this any binary data. So let's just use a noise texture for that and see how this looks. And make sure that you set the width and height to the same as the grid width. And we'll just make a new fast noise light. And there we go. So we have a dot matrix display that can display a black and white texture, but it's a little meh. So let's juice it up with some glow. And for that, we need to make a new world environment node. So we'll just come up into the scene tree. We'll find that and throw one in. And a world environment node requires an environment. So let's just make a new. And make sure that we set the background to canvas. Then we'll just come down to the glow, enable it. We'll zoom in. And then we'll just play around with these values until we get something that we like. And that's the rendering taken care of. But the next thing we have to do is talk about how we're actually going to run this simulation. Before we start writing our processing logic for the simulation, we have something to consider. The memory footprint of our data set isn't large enough to be relevant, but the number of operations required to process the entire data set very much is. So what do we know? We know our grid width is 1024 pixels. And because it's 1024 pixels, we know that we have 1024 squared individual data points within that set. And these all need to be processed inside of a single frame. So even if we simply swapped all of the zeros to ones and vice versa, that's a lot of operations and still far fewer than we need to create the simulation. So let's take a look at some of our options and see if we can figure out what the best way to do this would be. Regardless of which language you use or what logic you write, instructions have to be executed on threads. We could try to process the data set in a single thread on the CPU, but like using a tile map for the simulation, this will destroy our performance. So what can we do about this? We can split the data set into smaller subsets and process those on different threads in parallel. This will dramatically increase the performance of our logic. However, the size of those sets will be constrained by the number of parallel threads our CPU can handle, which isn't really ideal if we want real-time processing. Fortunately, there's another component in our computer that we can leverage to process all of this data just as fast as our shader allows us to render it. There's a reason that AI companies and crypto miners buy up all the GPU stock. GPUs are purpose-built for exactly this kind of thing, and there's a special kind of shader that we can use for executing logic that isn't related to rendering. It's called a compute shader, and that's what we're going to use. Alright, back in Godot, the first thing we have to do is actually make this compute shader, and it's going to be a GLSL file. And the thing about working with compute shaders in Godot is that as of version 4.1, it doesn't actually allow you to create that file from inside the editor, and you can't edit GLSL files in Godot either. So we're going to open our project in the file manager, and we're just going to create a new text file. And then we'll name this gameoflife.glsl. We're going to get this little message that asks us if it's okay to change the extension, and it is. And then once you've done that, you just want to open this up in your IDE. Alright, we've got our file open, but before we start writing any code, we want to address something first. And that is the fact that your IDE probably does not have support for GLSL. So you're not going to get your IntelliSense and you're not going to have error checking. You can download plugins for this, which I've done with Rider. And it's just this one right here. And you can find plugins that give you some of this functionality for VS Code and Visual Studio as well. But none of them are actually that good. We're just going to take it slow and be very deliberate with our coding here because debugging GLSL is honestly kind of painful. Now that we have some basic support for GLSL, let's just start filling this file out. And the first thing we need is this line up top. And this just tells Godot that this is a compute shader. And this causes an error, so I'm just going to comment this out for now. The next thing we have to do is set up the version. We just type hashtag version, and it's going to be version 450. Great. Now let's start setting up some variables here. We're going to need that variable for grid width, just like in our shader, and it's going to be the same value of 1024. We're also going to need a couple of colors, one to represent a live cell and one for a dead cell. And this is just white here, so we'll do the same for the dead cell and make it black. And these values are RGBA, so it's RGBA going across, and the last value is the alpha value. And now we need a layout variable, and this is going to be for our invocations. And we said that we were going to talk about invocations a little later on. We're getting to that now. Invocations is just a fancy way of saying threads. Invocations are just threads for your GPU. And those threads run in three-dimensional space. So you have X invocations, Y invocations, and Z invocations as well. So let's go ahead and set this up. And we're going to set that size to 32. And on the Y, 32 as well. And just one on the Z axis because we're working in two-dimensional space. And we just put IN at the end here. All right, the next thing we need here is a couple more layout variables for our input and output images. And this is going to be restrict, uniform, read only for the input image. And it's going to be an image 2D. And we'll just call it input image. And we're going to need something similar for the output, so we can just copy that line. We'll change the binding to 1. And instead of read only, we want write only. And rename it to output image. Great. Now let's set up a helper function that's going to check if the cell is alive. So first we're just going to get the color of the pixel at this position. And then we'll return a Boolean value that tells us if the value in the R channel is greater than 0.5. Great. Now we need to set up another function that's going to check how many of the neighbors of this pixel are considered alive. And that's going to take in the X and Y position as well. And the first thing we have to do in here is initialize some sort of counter. So we'll just say int count and just set that to 0. And now we have to loop through all of the pixels that this particular invocation is going to be responsible for. So we need a couple of loops here. We'll just say for int I equals -1, I is less than or equal to 1, and I++. And we'll do the same thing except for j. Great. Now inside here, we want to actually get the index of the neighboring pixel. So we'll do that with int nx equals x plus I, and ny will be y plus j. Okay. And now we have to check if these coordinates are actually within the bounds of our binary data set. Now we're going to get that pixel color again for this neighbor cell. And we'll be taking that from the input image and passing in that IVEC2 with the coordinates. We want nx and ny because we're checking the neighbor. And then we'll just say count plus equals int is cell alive, and just pass in our nx and ny here as well. Great. All right, one more thing before we move down to our main function where we're actually going to implement the simulation logic. We just want to make sure that we're not including the current pixel as a neighbor of itself. And we'll just continue here. Okay, so all the logic for the simulation is going to run inside of this main function. It's just going to be void main. And the first thing we're going to do in here is get our pixel position from the global invocation ID. And the next thing we want to do is check that that position actually exists inside the bounds of our grid. And we'll just continue if it isn't. Okay, now we're going to set up some variables inside this function. And the first thing we're going to do is get the count of the live neighbors. And we're going to use our helper function for that. And we'll just pass in position.x and position.y. And the next thing we're going to do is cache a value to store the state of the cell, so if it's alive or not. That's just going to be a bool is alive, and it's going to be equal to is cell alive, and we'll just pass in our position.x and y again. And now we're going to cache a value for the next state of the cell. Just like that. And this is where we're going to actually implement the rules for the simulation. So if you remember from the intro, I said that there were 3 rules. And the first rule is that if a cell is alive and it has less than 2 live neighbors, it will die. If a cell is alive and it has more than 3 live neighbors, it will also die. But if a cell is dead and it has exactly 3 live neighbors, it will become alive. So let's implement that with a couple of if statements here. And we'll just say next state equals false. And else if not is alive. And live neighbors is equal to 3. We'll say next state is true. So pretty simple there. And now we're going to get a value for what the new color should be. And we'll just use a ternary operator here. Perfect. And the last thing we have to do in here is call this image store function. And we'll store in the output image at position our new color. And that should be it for the actual GLSL code. And like I said, IntelliSense and error checking is basically non-existent here, so just be very deliberate when you're writing this code. If you don't feel like writing it yourself, you can just grab it from the GitHub. It's all going to be up there for free. This code in and of itself won't actually do anything. Most shaders are dispatched as part of the graphics pipeline, but compute shaders aren't associated with the graphics pipeline, so we're going to have to handle that dispatching ourselves. Alright, so back here in Godot, you might see an error. It says gameoflife.glsl contains unrecoverable errors. This is because we commented out that line at the top of our file. If you want to remove this error, and you'll have to, just uncomment that line and everything should work fine. So let's go ahead and make a dispatching script for our shader. We'll just go to new script, and it will be of type C#. And we'll just call this dispatcher.cs. And go ahead and open it up in the IDE. All right, with our file open, the first thing we're going to do is modify our using statements a little bit. We don't need system, but we will need Godot.collections. We're also going to be using system.threading.tasks. Perfect. Now we're going to throw some variables in here, and we'll just talk about them as we populate the list. So we're going to have a group, and we're going to call that group settings. And the first variable in that group is going to be called update frequency. And this is going to control how often our shader simulation actually updates. And this is times per second. So this is 60 times per second by default. The next variable is called auto start. And this controls whether or not the shader will start the processing loop immediately when you press the play button. The last setting is going to be our data texture, which is our binary input data. We also need a group for our requirements. And the first requirement we have is a reference to our compute shader. And the second requirement we have is going to be a reference to our renderer sprite. We're also going to need a rendering device, and we're going to need a few resource IDs. We'll need one for the input texture, one for the output texture, one for our uniform set, one for our shader, and one for our pipeline. And we're going to need a few uniforms as well, an input uniform, an output uniform, and an array of uniforms that we're going to call bindings. We'll also need an image for our input image, an image for our output image, and an image texture for our render texture. And then we'll need a few RD texture formats, one for the input format, as well as the output format. And we'll have a private bool for processing. And this will tell us whether or not the simulation is currently processing. And lastly, we just need one more variable for our texture usage bits. And we'll need storage bit, can update bit, and can copy from bit as well. And with all the variables out of the way, let's just start filling out some of our logic. And we're going to need a few of the main loop functions. So let's make a region for that. And we are going to need the ready function. We're also going to need the input function. And we are going to need the notification function. And we'll just leave these empty for now and come back and fill them out later. All right, the next thing we're going to do is open up another region. And this is going to be for our image setup. And the first thing we need in here is a private method called merge images. So it'll be private void, and we'll call that merge images. Great. And what we're going to use this for is to merge the pixels from the input image with the output image. And if the input image is smaller than the output image, we're going to merge those pixels into the center. So let's just start quickly filling this out here, and we'll talk about it as we go. So we're going to have to cache our output width. And that's going to be output image.getWidth. And we'll also need the height. And we'll have to do the same for the input. Great. Now the next thing we need to do is calculate where we're going to start this merging operation from. And that's easy enough. So now we're going to loop through all of the pixels in the input image and merge them onto the output image. And we'll do the same for the Y. And the Y considers the height instead of the width. Great. And in here, we're first just going to get the color from that input image. And we'll use getPixel for that. And we'll pass in our coordinates of X and Y. And the next thing we're going to do is get the destination X and destination Y. All right, now we just want to make sure that this pixel is in bounds. Perfect. And inside of this if block, we're just going to set the output pixel there. So we'll use output image dot set pixel, and we'll use dest X, dest Y, and color. Pretty easy. And down here outside both of these for loops, we're just going to set that input image data. And we do that just like this. We just call this input image dot set data and pass in the width and height of our grid. Use mip maps, we're going to set to false. The image format is L8, which stands for luminance 8 because this is only a single channel image. And the data is going to be the output image data. So we're taking the input image, merging it with the output image, and then setting the data of the input image to that new image. All right, and with that out of the way, we need another method. This is going to be a private void called link output texture to renderer. And what this is going to do is link the output texture to our renderer's shader material. And that's pretty easy to do. So we'll just say shader material and call it mat, and we'll say that it's equal to underscore renderer dot material with the capital M as shader material. And then we need to say underscore render texture equals image texture dot create from image. We're going to use our output image. And lastly, we just want to use mat, little question mark here for the null check, and we will set shader parameter. And the name of the parameter is binary data texture. And this is case sensitive, so make sure that you pay attention to that. And we will set it to our render texture. And that's it for that one. So the next method we're going to need is going to be called create and validate images. It's also going to be a private void. And what this method is going to do is create our output image, validate our input image, and if the input image is null, it's going to use a new noise image generated and set that as the input image instead. So we'll just say output image equals image.create, and it's going to be 1024, 1024, false on the bitmaps, image.format, and the format will be L8. Great. And the next thing we need is to check if that data texture is null. And if it is, we're going to create that new noise image. So fast noise light, noise, and that's going to be equal to a new, and we'll just set the frequency like this to 0.1f. And after that, we'll just say image noise image equals noise.getImage. And we'll pass in our dimensions. And that should be it for that. And lastly, we'll just say that the input image is equal to our noise image. And then we'll put a little else on here. We'll just say input image is equal to underscore data texture dot get image. So if we already have an image, we'll just use that. But if we don't, we're going to use this noise instead. We also need to add a few more calls in this method. And the first thing we're going to do is call that merge images method. And then we're going to call that link output texture method. And that's it for that. That's all we need for the image setup. All right, with the image setup out of the way, let's come down here and make another region. And this is going to be for our shader setup. And in here, the first thing we need to do is create a private method, a void return type, and it's going to be called create rendering device. And this is one line. So rd equals rendering server dot create local rendering device. And that's all we need for that. We're also going to need a method to create our shader. So that would be private void. We'll call it create shader. And it does exactly what it says. And the first thing we're going to do is make a new rd shader file. And we'll just call that shader file. And set that equal to gd.load. And we'll pass in the type of rd shader file. And we'll just use the compute shader path that we set up in the variables. And the next thing we have to do is actually get the spur-v code. That's going to be rd shader spur-v, and we'll just call this spur-v and set that equal to shader file dot get spur-v. And the last thing in here is we'll just say shader is equal to underscore rd dot create shader create from spurv. And make sure that we pass in our spurv code. All right, one more method here. It's going to be a private void called create pipeline. Again, this does exactly what it says. And this is another one-liner. We'll just say pipeline equals underscore rd dot compute pipeline create. And we are going to create that from the shader. And now we're going to set up a little helper method here because we're going to use the code in this next method a couple of times, and it saves us a few keystrokes doing it this way. It's going to be a private rd texture format, and we'll just call it default texture format. We don't need that. We'll just set up a lambda here, and it's going to return a new rd texture format with these parameters. We'll say that the width is equal to 1024. We'll say the height is the same. We'll say that the format is equal to rendering device dot data format and dot r8 unorm. And lastly, the usage bits will be equal to that texture usage variable that we set up. Great. And now we need a method for creating the texture formats, and that's just going to be a private void called create texture formats. And we'll need the input format and set that equal to default texture format. This is why we made the method. And the output format as well. And that is the same. Great. Now we're going to make a method called create texture and uniform, and it's going to return a resource ID. This actually has to take in some parameters. We're going to need an image, and we'll just call that image. We're going to need an RD texture format, and we'll call it format. And lastly, an int for the binding. The first thing we're going to do in here is get a new texture view. So RD texture view. Just call it view and say that's equal to new. And next we're going to retrieve the image data and store it in an array. So we'll say array, and that will be an array of bytes. And call it data and say that that's equal to new. And we'll say image.getData. And the next thing we need is an RID for our texture. And we'll just call it texture. Set that equal to rd.textureCreate. And pass in our format, our view, and our data. All right, the next thing we need to do is initialize a new uniform for the texture. So that's just going to be rd uniform. And we'll call it uniform and say that it's equal to a new. And pass in some parameters here. It will be uniform type will be equal to rendering device dot uniform type dot image. And we'll also set the binding. And the binding will be equal to that binding variable that we're passing into the method. Let's just make sure we get this semicolon here. And next we'll say uniform.add ID. And we'll pass in the texture. And we'll say bindings.add and pass in the uniform. And lastly, we will just return that resource ID for the texture. Okay, we're going to need another method. It's going to be a private void, and we'll call this create uniforms. And we need the input texture. So we'll say input texture equals create texture and uniform, and we will pass in the input image, the input format, as well as the binding of 0. And then we'll do the same for the output texture. We will use the output image, the output format, and pass in a binding of 1. And last thing in here is we will just define our uniform set. And that's going to be equal to _rd dot uniform create set, uniform set create rather, and pass in our bindings, our shader, and our shader set, which is 0. Great. And we need one more method in here. It's going to be a private void. We're going to call it setup compute shader. And this is basically just going to call all of the methods that we just created in the right order. So first we'll create the rendering device, and then we'll create the shader, and then the pipeline, and then our texture formats, and lastly the uniforms. Just like that. All right, with all of the setup code out of the way, the last thing we have to do in here is implement our processing and cleanup logic. So let's just put that inside another region. We'll call this region processing. And the first method we're going to have is going to be a private async void called start process loop. And in here we will say int frq for frequency equals 1000 divided by our update frequency. And then we will just say that processing is equal to true. Next thing we're going to do is create a little while loop and say while processing. We're going to do whatever's inside of here. We're going to call a method called update. We'll make this in just a second. And then await task.delay, and we will pass in our frequency. And then we'll call a method called render. And that's all we need in there. So let's make that update method. It's just going to be a private void. Call it update. And the first thing we need is a long, and we'll call this compute list, and set that equal to _rd dot compute list begin. And next we'll just say rd dot compute list bind compute pipeline. And we will pass in our compute list and our pipeline. And next we'll use _rd again. And we're going to bind our uniform set. So compute list, bind uniform set, and pass in the compute list, as well as that uniform set. And it needs a set index, which is just 0. And then we'll say rd.computeList dispatch, and pass in the compute list. And now we need X groups, Y groups, and Z groups. And if you remember when we were writing the GLSL, we set the X and Y groups to 32. And to make sure that we account for all of the pixels in the image, we have to set these to 32 as well. If you use different values, you'll have to do the math to calculate what the size of this needs to be. but for our use case here, these are the numbers that work. So lastly, we have rd compute list end, and finally rd.submit. And this is what's actually going to dispatch our shader code to the graphics card. So let's just set up this render method real quick. And in here we will say rd.sync, and this is how we sync the graphics card back to the CPU after all of the processing is done. And we'll say byte, array of bytes here. We'll just call this bytes. And that's going to be equal to underscore rd.texture get data. So we're actually going to pull the texture back from our compute shader. And we'll use output texture on layer 0. And then we'll say underscore rd.texture update. And we're going to update our input texture on layer 0 with our bytes from the output texture. The next thing we have to do is say that output image dot set data, and we'll pass in 1024, 1024, faults on the bitmaps, image dot format, and L8. This is the same as everywhere else we've used it, and pass in our bytes here as well. And lastly, in here we will just say underscore render texture dot update and pass in our output image. And that's it for that method. We need one final method here, and that's to clean everything up so that we don't get memory leaks. So that's going to be a private void called cleanup GPU. And in here, we'll just check if rd is null. There's no reason to clean it up if it is. So if rd is null, we'll just return. And then we'll clean up all of our resource IDs. And you use free rid for that. And we'll need to do that for the input texture. And we'll just copy this a couple times. We'll also want to clean up the output texture. We'll want to clean up the uniform set. We'll want to clean up our pipeline. And we'll want to clean up our shader. And we are also going to call free on rd. And lastly, we'll set rd to null. And that is it for the processing logic. So let's go back up top and start filling out those main loop functions. All right, so let's start with ready. And the first thing we're going to do is just call that create and validate images method. Then we're going to set up the compute shader. And we'll just do a little check for the auto start. And we'll say if not, underscore auto start. We'll just return. And if it is auto start, we will actually start the process loop. Then we'll come down into the input function here, and we'll just say if event is not input event key, and we'll call that key. We'll just return. So if this isn't a keystroke that's been detected, we don't want to do anything. But if key.keycode is not equal to space, key.space, or not key.pressed, I'm going to return here as well. So we're only detecting input on the spacebar, and we only want to detect it when the spacebar is pressed. So another little check here, we'll say if we're already processing, we're going to stop the simulation. So we'll say processing is equal to false, else we're going to start the simulation. And we just do that by calling start process loop. And that's all the input detection we need. And this last method here for the notification, this is pretty easy. So we'll just check that what value. So if what is equal to notification WM close request triple equals. That's very equal. Or what is equal to notification pre-delete. Then we're going to call that cleanup method. And that should be all the code that we need for the dispatching. Back into Godot, we got a little bit of setup before we can test this out, but it's pretty easy. We're just going to come up to the scene tree. We're going to make a new node. It doesn't have to be 2D, 3D, it doesn't matter. Just a normal node is fine. And we'll rename this to dispatcher. And we're going to drag that script we just created on. And there we go. If you don't see these settings and requirements here, you may have to press the build button and then they should show up for you. We don't have to pass in a data texture because we'll just get noise if we don't. We'll have to drag in the reference to the GLSL file. And we'll also have to drag the reference to our renderer. All right, before we actually go back into Godot and test this out, I just wanted to come and have a second look at this shader code just to make sure that everything's correct. And it's a good thing that I did. I forgot to return the count here. And we also can't continue because this isn't inside a loop, so we'll just want to use return here instead of continue. And we will remove this comment so that Godot recognizes the compute shader. And we'll go give that a shot. All right, the noise appears to be working. And if we press spacebar, we should be able to see our simulation. And that appears to be working as well. If you guys find this content helpful, please consider liking and subscribing. It really helps out the channel and it helps to get these videos in front of the people that need them. And I will see you guys on the next one. Take care.